Welcome back to ECE 320A. Your homework number 7 is due today, and I can see that most of you are turning that, or have turned that in already from the stack on the front of the room. The review for exam number 3 will be Monday. It will be before we meet again. Today's Thursday, correct? In a week, you have your third exam in here. Prior to that, we'll have our review session Monday afternoon at 4. That will be in ECE room 530. We will then have homework number 8 due. You really, after today's class, should have enough background to work homework number 8. It is dealing with problems in chapter 14, which is a filtering chapter, but it's basically how do you analyze these filters. It's not asking you to design any filters yet, but it's trying to get you to understand how these circuits respond, and hopefully that will get you up and somewhat moving relative to filters, which we will get into after exam number 3, which again is a week from today. What I want to do today is review very quickly. I've already written these notes down, so I'm just going to scroll down the page really quick on how to obtain the sinusoidal steady state output response for the Y in terms of the transfer function H of S and the input exciting waveform X of t, when X of t is a cosine waveform. We'll look at a couple of examples of that. We'll start with a circuit and look at that problem. Then we'll just be given a transfer function and say, okay, find how this system, whatever that system represents, behaves in the sinusoidal steady state. And how long will it take us to get to the sinusoidal steady state? 5 time constants. What if we have 6 real poles? Which pole would you be interested in or focusing on if you wanted to do a crude approximation quickly? You now have 6 poles. Maybe they're at -2, -5, -7, etc., beyond to the left of -7 to complete the 6 real poles, and you excite your system with a sinusoid. Which pole do you examine? The one closest to the origin. That's the slowest pole, and that has the largest time constant, and you would then look at 5 of those time constants. Is that clear? So you're waiting for these transients to decay, and that in electrical circuits doesn't take very long, and that's why we a lot of times concentrate on sinusoidal steady state. That's why you spend all that time before this class at the end of 220 dealing with phasors and analyzing circuits in the sinusoidal steady state, because it does have bearing, or it does happen quite frequently. Then we will look at plotting these transfer function poles and zeros in the S-plane and understanding how we can, from those pictures of S-plane plots of poles and zeros, determine graphically this complex number or complex expression for the transfer function evaluated at a particular frequency omega naught. So now we're going to the circus. We will be walking underneath the circus tent on the imaginary axis, and that's where we are walking. And if we want omega naught equal to 1 radian per second, we go up to J1. If we want omega naught of 4 radians per second, we walk up to J4. And from that vantage point, we look at how the poles and zeros contribute information to us, and that will give us actually a way of calculating this complex number, h of J1, h of J4, depending on omega naught. And omega naught is which frequency? What might identify omega naught? That's how fast we're shaking it, or what frequency we are shaking. That's the input's frequency. You have X having cosine omega naught t. That omega naught is how fast or slow you are shaking that particular system. That's the omega naught, which, if we get there, if we got into Fourier series, you might have signals x that are composed of all sorts of sinusoids, and we might like to know, how is this system going to behave at 1 radian per second, at 2 radians per second, at 3 radians per second. So we march at J1, J2, J3, and we can tell how the system then will respond to each of those frequencies once we know this information. Yes? And you can do a superposition. The comment was, can you use superposition? We are dealing with linear systems, and now if we have x of t made up of 5 different sines or cosines, we can look at each of those sines and cosines individually and then add up their result. And that's really what you're doing in Fourier series. You have a periodic waveform, and it can be described by a collection of sines and cosines. And if we know how systems respond to sines and cosines, we basically know how to solve problems that are excited by periodic waveforms, or systems that are excited by periodic waveforms. That's one of the reasons why here, so you'll have to just read this. I think I got, using H of S to obtain the sinusoidal steady-state output response. Here is the picture, and like I said, I'm going to quickly scroll through this, but this is the idea or the concept that H of S might come from a circuit. In this class, it probably will. You know how to find that H of S. You identify the output terminal and the input location and find the transfer function between those 2 points. That's your H of S, and a circuit could have 3 or 4 different transfer functions associated with it. You then apply an input, which, if you can Laplace transform it, gives you this capital X of S. In the frequency domain, if we're playing there, we simply multiply the system's transfer function by the signal's transform to obtain the transform of the output waveform. That gives us capital Y of S. Once we have Y of S, in this case, we are going to assume H of S is stable. If it wasn't stable, then if we start shaking an unstable system, it's going to blow up, burn up. It's going to be destroyed, or it's going to saturate. Something will happen that we don't like, probably, if we shake an unstable system. So we're going to assume our system is stable. H of S then has all of its poles in the left half plane. And what we want to do now is excite that system, that stable system, with a sine wave. In this case, that sinusoid is a cosine. It has an amplitude of A, a frequency of omega naught, and it's actually, for generality's sense, has a phase shift of phi. That's what we're exciting our linear system with. We're hitting our system, capital H of S, with that sinusoidal signal. And we know if we wanted to find the total response or the complete response, we could simply form the product of H and X and get Y, and inverse Laplace transform that capital Y to obtain the total response, Y of t. We're not interested in that. We're going to go ahead and just assume that we're only interested in the sinusoidal steady state response, and we're going to separate that output into the 2 pieces. One piece due to the transients of the poles of our H of S, and the other due to the poles associated with capital Y sub SS. And where are those poles going to be located? If those correspond to our sinusoidal steady state output response, do we know anything more about those? They're on the j omega. That's our signal that's exciting our system, and by the definition of that sine wave, sinusoid, which is a cosine, it's going to be having a pole plus j omega naught and minus j omega naught. All we are interested in at this point is finding this piece that's associated with the sinusoidal steady state. That's the only piece that we're worried about. And we want to do that without finding the total or the complete output response. We don't want to go ahead and find all of these partial fraction expansion coefficients in the product of H and X and inverse Laplace transform all of those. We want to just focus on the two that are associated with the complex poles at plus and minus j omega naught. Let's now develop the expression for that process so that we can then use this. So you won't have to rederive this. On the exam, you simply just need to use it. And this is sort of where we stopped, I think, last time a little bit, but I tried to coach you on through that. And this was in some section of the book, I think section 7 of chapter 13. Assuming x is this cosine waveform, we are going to expand that using the trigonometric relationship for the cosine of the sum of two angles. And we can then identify really some weights or coefficients associated with the cosine term and a weighting on the sine term. And now we know how to transform cosine and sine. We know how to Laplace transform those pieces. The cosine is this s over s squared plus omega naught squared. The sine piece is the frequency over s squared plus omega naught squared. That should be okay. You should be comfortable with that. We haven't done anything magic at this point. If that is our input, we want to then hit our system with that input. We're going to then substitute capital X of S with that structure, and now I've put them over the same common denominator. The denominator is the same for both of those pieces of the sine and cosine piece. And remember, this s squared plus omega naught squared, you just told me, is associated with the poles. Where is this pole located? Or where is the pole associated with this first factor, s minus j omega naught? Where is that pole? That's at the plus. That's in the upper half. You set that term equal to 0, and you see that s is equal to plus j omega naught. The one on the right is one in the bottom half of the s-plane. We can then think of this entire collection. Remember, capital H of S could have all sorts of stable poles, and those don't have to be real. They could be complex. But H of S, all of its poles are in the left half plane, which means that they have these decaying exponentials associated with them when we take them into the time domain. They have these e to the minus sigmas. What we're going to do is simply forget about those, because those are going to be transient in nature. That's why the subscript tran. Those will decay after 5 time constants, if we approximate the time constant as the slowest time constant. And it may be a little different, but let's for now just say we're going to neglect those terms. They're all going to disappear eventually, and all we want to do is concentrate on the first 2 terms in this partial fraction expansion for capital Y of S. And if we can find K sub 1, then we can basically inverse Laplace transform capital Y sub SS to obtain the answer that we need. That's all we're looking for. Is it clear where that bottom expression is coming from? That's just the partial fraction expansion, and I didn't explicitly define capital H of S. I just said it has stable poles, and so I'm not even going to worry about the remaining terms in that partial fraction expansion. They will all decay with time. What we want to do is find K1, and we use exactly the same formula that we've been using all along to find that partial fraction expansion coefficient for K sub 1. We multiply y of s by the factor that includes or contains the pole of interest that's associated with K1. This is the factor associated with that upper pole, and for that reason we evaluate that resulting expression at that location, at j omega naught, when s is equal to j omega naught. Let's now replace y with what we've already defined it to be. But once we've multiplied that y by the s minus j omega naught, the denominator now becomes simplified. We've now canceled a half of that, or a piece of that denominator, and we're just left with the factor associated with the pole down in the lower half of the s-plane. That's all I've done in this line below the green line. And K1 then, if we can simply evaluate this expression, will be what we need. If we now replace all the s's with s equal to j omega naught, we're now evaluating right on the imaginary axis. H of s becomes h of j omega naught. If omega naught was 3 radians per second, we would simply plug in omega naught equal to 3. And we would evaluate this transfer function, capital H of s, at h of j3. We would replace all of our s's in the numerator, all of our s's in the denominator with j3, and find the complex number that comes out. And that would be our h of j3, which in general is going to be a complex number. Likewise, we have j omega naught in the numerator that scales the cosine coefficient. We don't have to worry about the sine coefficient, but on the denominator we have j omega naught plus j omega naught, or we have two of those pieces. And we can actually clean that expression up, by simply realizing that minus 1 I can rewrite as j squared. And doing that, I can now replace this minus omega naught term in the numerator expression with a plus jj omega naught. And I have a j in all three of those terms. I can cancel those. I can cancel the omega naught, and now I'm left with just one j piece and a plus sign in the numerator. And I've gone ahead and factored the amplitude of the cosine waveform out of everything in the brackets. So my capital A, which was the amplitude of my x of t, is now at the far left of that expression. If I pull that 2 out from the curly bracket, everything else in the denominator is gone. I just have a number 1 in the denominator. The denominator is gone. In the numerator, I'm left with just cosine of phi plus j sine phi, and that's begging me to say that's e to the j phi by Euler. And now I have a concise expression for this partial fraction expansion coefficient, k sub 1, that I was looking for. I simply have it in terms of the amplitude of my exciting input signal, capital A. Phi, remember, was the phase of my x of t excitation, and h was the system that it was being passed through. I have all of that information available to me. That's all given, And omega naught is the frequency of the sine wave or the cosine waveform that was being applied. Meaning I can now collapse this down to k sub 1 equaling a over 2. And this is obviously a complex number. And remember, h in general is complex. Because of that, I'm going to separate it into its polar form. I'm going to give it a magnitude, and I'm going to pull out its phase. And I'm going to call its phase theta, and it's a function of the frequency omega naught that we're evaluating the expression for. If you have a question about, well, is that an argument? Is it a variable? In this case, this is theta, which is has as an argument omega naught. That theta, that angle of the transfer function, is going to hinge on what frequency we're exciting the system at. And I'm trying to explicitly call that out by saying theta is a function of that frequency omega naught. If I now replace h in the K1 expression with this structure, polar form structure of H, I can now start to combine my angles. I now have K1 looking like this. It's A over 2 times the magnitude of my transfer function at j omega naught. And I have these two angles. Because they're associated with a complex exponential, I can combine those, and now I have phi plus phi plus theta. So that's my K1. And once I have K1 written that way, and since I'm just interested in a part of my total response, which is a sinusoidal steady state response, now I simply need to replace this k sub 1, that's the partial fraction coefficient, with this structure that I've now identified. And we've worked with complex K1s in the past. K1s generally can be complex if we have complex roots. So this shouldn't be foreign to us. It's just that now it's maybe a longer expression, but K1 now we can identify what it looks like. It's a magnitude at an angle. That's all we're saying. And the angle of that K1 is phi plus theta. How do I find the time domain y sub ss of t if I have capital Y sub ss? Inverse Laplace, which in terms of this K1, what would that, or just in terms of K1, what does that look like? If I gave you, I said, okay, here is, on the final exam, if I gave you this expression, and I actually gave you a complex number for K1, either in rectangular form or polar form, could you write down little y sub ss of t? And the correct answer should be yes. Yes, sir. I can write that down for an instant gift, right? Well, at least by the final, you better be answering that. Remember what it is? It's just this. We take 2 times the magnitude of K1, and then we change the argument of the cosine that's happening at omega naught by the angle of K1. Which, putting in the particulars that we've already put together, the magnitude of K1 was A over 2, so those 2's are going to cancel. And we're just left with the magnitude or the amplitude of that cosine being adjusted by how that system responds at the given frequency omega naught. That's the magnitude response of the system at that frequency. And all we have done with the original excitation, x of t, had an argument of omega naught t plus phi, we've now just had to adjust that phase by the angle of our transfer function at that frequency omega naught. And that's what I've tried to indicate here in red. Here is the result, and this is what you could have on your crib sheet. You just need to know how to use it on the exam 3 and the final. Is if I give you an input waveform that's a cosine wave, and I'm exciting a stable system, capital H of S, then you should immediately be able to evaluate what that transfer function is doing at the frequency omega naught. And you do that by looking at the imaginary axis and saying, what do these poles and zeros and the gain of my transfer function, capital H of S, do at this particular frequency, where the frequency is omega naught, made up of or determined by the frequency that we were exciting the system with, x of t. If we summarize that or conclude, then we have really two conclusions. Given an input, x, that's a cosine, or if it was a sine, you could do exactly the same thing, just make sure your y was a sine, or you could convert the x to a cosine and continue along your path. Now all we have done is determined that the amplitude of the input is now adjusted by the magnitude of our transfer function at that frequency, omega naught, and the phase of this sinusoidal steady state has been adjusted by the phase of our transfer function evaluated at s equal j omega naught. Questions on that? That was a quick slide through of the material, but we kind of covered it, and I wanted you, and you probably already have had to use this if you've completed your homework for today. You had to use this end result. Let's just convince ourselves that we know how to use it. Suppose that we look at the following circuit. Suppose somebody says, okay, I'm going to apply as an input voltage 5 times the cosine of 2t plus 45 degrees. And what is can I get any fancier with my subscripts? But that's supposed to be the output current, and I have to define that in my circuit in the sinusoidal steady state. That's what that's supposed to mean. Here's my circuit. Here's my input. I have a resistor, an inductor. I have an inductor and a capacitor. And I have an inductor and another capacitor. And this is the current of interest. That's my output current. The units on some of these elements, the resistor is 1 ohm, the inductor, all the inductors are 1 Henry, and the capacitors are 1 farad and a half a farad. This could be an exam 3 problem. I could say, okay, find what I sub O steady state is. Do you need to worry about initial conditions? No, because you're worried about the sinusoidal steady state behavior. Meaning you can immediately take this into the transform domain without worrying about the initial conditions, which if you worried about initial conditions and they were given to you, How many initial conditions would we have? 5. So we could have 5 different sources in addition to this external or this particular input voltage V sub I, if we wanted to really make it more interesting. In order to solve this, based on what we've just done, we need a transfer function. Where H of S is actually this output currents transform over the input voltage Laplace transform. Pardon? And well, if it's sort of it's 1 over an impedance, but now we have to worry about what that impedance is. And it actually makes for a slightly easier problem if we do a source transformation on this piece. Meaning if we find the Norton equivalent of that, now everything will be in parallel, and we can now find the rightmost current in that parallel configuration. Is that making sense? You can solve this however you want. You could do a KCL equation right now at the top if you wanted, and it won't be that much different. But if we do a source transformation, and at the same time go into the S domain, we have our input voltage source divided by the impedance, the series impedance, which now we want to keep it in the S domain. And our inductors have what for their impedance? SL. So it's S times 1, so the L goes away, or it's not very explicitly there, but it is there. So we have S plus 1 for that impedance. That now needs to come here and divide our expression for the input voltage waveform's Laplace transform. Then we have that particular impedance. Here's the 1 and the S. Then we have this, which was S, and this was 1 over SC. And on the far right, again, we had an S, and this was 1 over SC, but here C was 1/2. So we end up with 2 over S, and we're after that particular current, which now we can find quickly if we simply call this node our output voltage node V sub 0, solve for it, and now I naught will be V naught over that impedance in the rightmost branch, which is S plus 2 over S. Meaning, if we did a KCL at this point, we have let's say we have V sub I of S over S plus 1 going in, and now coming out, we have V naught of S over S plus 1. We have V naught over S plus 1 over S plus a V naught over S plus 2 over S. Is everybody okay with that? I'm going to spare you the algebra and now write down the answer. Or maybe, yeah, I naught is simply V naught of S over S plus 2 over S. Which is actually S V naught of S, S plus, should say, S squared plus 2. So if we solve for V naught of S, we can now find the output current I naught, and H is simply I naught over V sub I. So H is I naught over V sub I. I want you guys not to be bored tonight, so you can go through this algebra. And you end up with the following. You have S squared plus 1, and here you have 3s to the 4th plus 2s cubed plus 6s squared plus 3s plus 2. Where are your finite zeros? Can you see where those are located? Where's one of your finite zeros? At the origin. So you have a thumbtack in this system at the origin. Then you have zeros at the roots of s squared plus 1. What are those providing or producing? Plus and minus j1. So now we have 3 zeros on the imaginary axis. One at the origin, and then complex zeros at plus j1 and minus j1. And the denominator is a little bit more ugly, but you can factor that if you wanted to. And it ends up being, they're all 4 in the left half plane. They're not too far into the left half plane, but they're at minus 0.318 plus and minus j 0.57 and minus 0.015 plus and minus j 1.245. If that, I'm sure that was understood. Here's where they are. We have a 0 here. We have another 0 at j1 and another 0 at minus j1. And our poles are at minus 0.318 plus and minus j 0.57. And the other one was very close to the imaginary axis, but not quite on it, about right there. So that's what our pole 0 pattern looks like for that capital H of S. All 4 of our poles are in the left half plane, which is what we want in order to apply this technique that we just discovered. Now I want to find the steady state output, sinusoidal steady state output current in that circuit, given the input voltage of, I don't remember, the 5 times cosine of 2t plus 45 degrees. So now what do? I didn't need that pole 0 pattern, but I just thought we need to get used to looking at that. It's kind of pretty. It tells us it's stable, and yes, so if you didn't know where those roots were in that 4th order, you would have to find those roots. And if somebody now sketches you this pole 0 pattern, you'd go, oh, I can actually apply the technique we talked about in class because H is stable. If those poles, if one of those poles, it would only take one. If one of those poles, if one was real in the right half plane, you couldn't do what we've just derived. Is that clear? Because you would not be at a stable, you would not, your transients would not decay, something would go unbounded with time, and you would never reach a sinusoidal steady state. Now what do we do, though? What are we interested in? We were given an input. Whoops, it wasn't x this time, was it? It was v sub I. V sub I of t was 5 cosine 2t plus 45 degrees. And we want I sub 0 steady state of t. What do I need to do? Okay, we need to find our transfer function when we replace s with j2, where that 2 is the frequency that we're exciting our waveform at. That's where that 2 comes from, meaning we now need to find h of j2. And in our particular transfer function, h of j2 becomes, we have an s there, so we replace that s with j2. We had an s squared there, and then we had that fourth order denominator. And there probably needs to be a square right there. Yes, thank you. And you've already computed that, right? You guys are quick with your complex algebra. You can compute that. It actually ends up being 8. Hopefully you see that it could potentially be a complex number. The numerator simplifies to minus 6j. The denominator is 26 minus j10, or it's 0.0773 minus j 0.201. And maybe we actually want that in polar form. I'm sorry? See, I told you you'd have trouble with my notation. I'm not even sure where you're having problems, but I'll move on. Something about 2's and squares. It's been a long day. But hopefully you can see that this imaginary piece is much bigger than your real piece, and so our angle is going to be bigger than 45 degrees. And it's not an, oh, and it's also down, isn't it? It's negative. So we're now going below an angle bigger than minus 45 degrees. So that sort of makes sense, and it's not too much larger than 0.2, which is the major component of our rectangular form of h of j2. But h, our transfer function, is a complex number at that frequency. With that information, we can now simply write down our answer. And that says we have 5 times this magnitude of our h, which is 21.5% basically of what we started with in amplitude, cosine. We haven't changed. This is a linear system, so it's going to be shaking everywhere at 2 radians per second. We have a cosine of 2t. We started with a 45-degree offset, and now we're taking away from that original position 69 degrees. Or if we multiply this out, which I'm not even sure this is going to be right because it's off my paper, but this is now cosine of 2t and that's now our sinusoidal steady state output current based on an input voltage waveform in that particular circuit, which was a, How many energy storage elements did we have? 5. So we had a cancellation, didn't we, somehow? We ended up with a fourth order denominator. And the way that circuit was laid out, you can kind of expect maybe you might have something weird going on because you have inductors and capacitors sort of in the same structure, maybe just slightly different values. But this is now our output current for that particular circuit in the sinusoidal steady state. Yes? So now the question was, with this angle being negative, what does that tell us? And now we have to remember back, what in the world are we asking? I think you're asking for leading or lagging angle. So now what was our original voltage? It had a plus 45, and now we have an angle that's minus 24. This is lagging by how much? Minus 69, the original voltage. So this would be an inductive looking circuit overall, even though we had 2 capacitors and 3 inductors. Obviously, it depends on their particular value, which was going to be more dominant. But in effect, in this transfer function between the input voltage and this defined output current, that particular transfer function looks inductive in nature. Question? Well, if we had, here we are going to, well, a lot of questions there. The question I'm not even sure I can summarize because I completely lost it already. Something about a passive circuit. It is a passive circuit, right? Because we have inductors, capacitors, and resistors, so it's inductive. What else was asked in the question? You asked about the angle. No, the question was, will the angle on H always be negative because of the time delay? No, if you actually had a capacitive looking circuit, it now may cause the current, well, this is now talking voltages, but it could cause one voltage to, in the sinusoidal steady state, so now just look at these 2 waveforms on your oscilloscope trace, and one relative to the other in the sinusoidal steady state, one looks to be ahead of the other. Whether or not it's really, I mean, do you get the idea? So now you haven't really worried too much about the transient. Now the transient is gone, and now you're saying, okay, in the sinusoidal steady state, at this location in the circuit, this particular voltage waveform is ahead of this voltage waveform. Does that make any sense? Other questions? That was coming from a circuit. Now that we have this concept of signals and systems, somebody could simply give you a transfer function, and maybe this transfer function is not associated with a circuit. It might actually be associated with some mechanical system. But now they give you a transfer function, h of s, and they say this is 1,000, s plus 5,000 over s squared plus 6,000 s plus 25 times 10 to the 6th. And let's say that they excite this system with a cosine of amplitude 120, a frequency of 5,000 radians per second, and a phase shift of plus 30 degrees. before we get too far into this, can you tell anybody whether or not it makes sense to do the analysis or apply the technique that we just talked about? We should be okay. Why can you say should be okay? So now remember what we were talking about with the second order. If somebody gave you a huge polynomial and they factored it into linear factors, real root factors, or complex factors, or quadratic factors, you could then tell them where their poles were located based on those well, no, you could basically say yes or no whether you could have some stable or unstable. What we talked about, let's now just assume that this coefficient is normalized to 1, so our polynomial is monic, M-O-N-I-C. That's 1. All we need for this second order polynomial to have roots in the left half plane, to have negative real parts, is for those two coefficients to both be present and positive. So they're present and positive. No. So the question was, would it only matter if this one was positive? If this was 0, okay, if this one is positive, now let's say this was 0. Now what do we have? In one of the extreme cases, you have a pole right at the origin, and that's no-no, right? Because I could excite that with a constant input and get a ramp out. So a system that has a pole at the origin is like an integrator as a system. And now if you integrate a constant for all time, what's going to happen? Well, that integrator will just keep adding and adding and adding, and you'll get a ramp. It's going to go unbounded. This represents some system, and in fact, because those two poles are present and positive, because those two coefficients are present and positive, we know we don't have to really explicitly factor it. We know that it's stable and we can continue. That's all we need to know, is that our H of S is stable. What else do we need to know based on this information? So H of S is stable. Now this is only true for a second order. If somebody gave you a third order and your coefficients were present and positive, it's not necessarily guaranteed that they'll all be in the left half plane. So you have to have it factored into second order or less. So that's coefficients are present and positive with the second order. Now what else do we need to know before we start crunching numbers? Or how do we start crunching numbers if we want to continue crunching or start crunching numbers? We know our frequency, don't we? What's our frequency of excitation? 5,000 radians per second. So now we know that omega naught is 5,000 radians per second, and that's all we need. Now we simply have to find what H is at J 5,000. And in terms of what we had 1,000 for a coefficient. We had S plus 5,000, and we replaced that S with J 5,000. And this cleans up pretty quickly. We now have 5 times the square root of 2 times 10 to the third, and plus another 10 to the third. So we have 5 times the square root of 2 times 10 to the sixth. at an angle of plus 45 degrees. That we can do in our head. The other one we might want to do some number crunching, but it ends up being 30 times 10 to the 6th at an angle of 90 degrees. I then end up with the square root of 2 over 6, and what's my angle? Minus 45. I can simply add and subtract angles when I'm multiplying and dividing these complex numbers. And now I can immediately write down my sinusoidal steady state output. I started with 120. I need to scale it up or down depending on what that number is. In this case, it's smaller than 1, so I'm going to contract my original input amplitude. Then I have cosine of 5,000t. I better not change the frequency that everything is shaking at because I have a linear system. I started with a 30-degree phase shift, and I take away 45 from that, and I now end up with 20 times the square root of 2 cosine of 5,000t minus 15 degrees, and that's now my sinusoidal steady state output for that given system that was stable, excited by a particular input waveform x of t. And that didn't take too much time. I didn't have to find the complete y of s and then let t go to infinity and see that all my exponent terms go away, the transients decay. You could. Now, if I tried to apply the final value theorem to that, what would you tell me? Huh? What? I can't tell anything, can I? Because I'm exciting this with a cosine. Is it ever going to settle to a final value? It's going to just keep shaking, isn't it? If I'm shaking it, and I can't move at 5,000 radians per second, so I'm not even going to try. Okay? But you get the idea. Let's now look at the next step in this, which is we've simply analytically been finding h of j omega. Let's see if we can put a visual to this. And see how to graphically determine this complex number, h of j omega naught. And let's just use the example that we finished with. Suppose we have our h of s is now 1,000, s plus 5,000. And I'm sure you all had already completed the square up above and realized that you now had complex poles in your denominator located accordingly to this particular factored form. Meaning, if we now want to sketch the S-plane plot of this, and you may want to be more accurate because you have to have the same scaling on your horizontal axis as your vertical axis if you want your angles to be correct. So it's critical that your scaling is accurate if you're trying to physically get angles from this picture. And now you can get out your protractor and your, well, now what do I draw? Here I'm now at the circus, aren't I? Now we can put in our poles and our thumbtacks. We can introduce our infinite poles and our thumbtacks. Where do I put thumbtacks? Negative 5,000, and I'm assuming that this is now scaled by 1,000. So here is minus 5,000. Here is my 0. And you'll maybe want to be a little bit better at your picture than I am. But now where are my thumbtack? I'm sorry, where are my poles? So now I go into the left half plane a distance of 3,000. So I'm at minus 3,000 plus and minus j 4,000. And I would like to be looking at this h of j omega, which is a magnitude and an angle. Now, don't forget when you're computing the magnitude, don't forget that gain that is there also. You have a 1,000 gain to introduce after you found the information that you are looking for from your poles and your zeros. But are we comfortable with this pole zero diagram from that transfer function so far? Now, what were we asked for in the previous example? We were wanting to find h at j 5,000. But if we're underneath, or if we're at the circus, we now can walk along this imaginary axis to find the frequency response if we look up at the height of that circus tent above us. What we want to do is start at the origin and walk up to j 5,000 and then see what you have above you. And we would also like to get angle information. So let's now walk to that location, and I will walk to that location and say that's the point of interest, h of j 5,000. And what we are going to do now is we will see that, in fact, we are interested in the following. We want to now look from each of these singularities to the frequency of interest. And that distance we would actually have to walk from the top x, from the bottom x, and from the minus 5, 0, that distance is actually associated with each of these factors in our transfer function. And the angle, if I now go over here and stand at minus 3,000 plus j 4,000, I'm going to have to rotate a little bit to see the j5. That's the angle that I'm going to have associated with that pole. If I now come down to minus 5,000 for my 0, and I'm measuring that angle with respect to the horizontal real axis or real line each time, I now have to turn a little bit wider to see j 5,000. And the angle of the 0 is this angle. And if you've drawn this accurately to scale, you could get your protractor out and measure that angle. Or you could then do it on your calculator, and you could say inverse tangent of 5 divided by 5. And that should be 45 degrees. Now you can go down to this guy and say, okay, here's my horizontal real line from that singularity. I now have to look up that much to see the angle contributed by this pole at minus 3,000 minus j 4,000. And if I calculated that analytically, I would have to then see 1, 2, 3, 4, 9, inverse tangent of 9 over 3. So the inverse tangent of 3 would be that angle. And those angles are all downstairs. They're in the denominator, so I'm going to subtract those from the upstairs angle. And what's the angle of the gain 1,000? 0. It has an angle of 0. It's a real number. So here are the angles that I'm going to be interested in. Here's, let's say, theta P1. Here is theta Z. And there's theta sub P sub 2. I'm also going to be interested in these lengths. This distance, this hypotenuse, I'll call LP1. This I will call L sub Z, since I only have one 0. And this length, or hypotenuse, I will call L sub P sub 2. Meaning, now I can, from that picture, actually think about what I have when I look at H of J omega. If that omega was something other than 5, it would be at some other location omega. And it's now 1,000 J omega plus 5,000. And downstairs, I have to factor this into my complex factors. I now have J omega plus 3,000 minus J 4,000. And I have J omega plus 3,000 plus J 4,000. So here is my 0 factor, and here are my 2 pole factors. And I can now associate a length or a magnitude with each of those factors and an angle with each of those factors. And if I want to know what's happening at omega equal to 5,000, I now have this number or expression, J 5,000 plus 5,000. That's my linear factor associated with the 0. Let me see if this makes any sense. I'll try to increase this in size. So if we look at the 0 factor, at that particular point, let's say that it's, well, let's just do it in general. I have a 0 at minus 5,000. And let's say this is now some number, J omega. So this was J omega plus 5,000. What I'm saying is I now have this length, L sub Z, and this angle, theta sub Z. Meaning I take this J omega plus 5,000, and if I start right here, whoops, suppose I start right here, and if I now move 5,000 to the right, I'm going to go there. And now if I go up J omega, I go orthogonal to where I was going, and I go up a distance of omega. And now I've actually traveled in the rectangular coordinates the same distance as my hypotenuse. And so I'm interested in that hypotenuse length, which is the square root of the square of those two sides. So I've gone over 5,000 and up omega, and now I can say that this is now the distance is 5,000 plus J, whoops. I need that magnitude, and the angle is the inverse tangent of omega over 5,000. Is that making any sense? So if somebody said, what's this 0 going to contribute if I excite my system with a frequency of 1,000 radians per second, this omega would be 1,000, and I would now be able to find what this hypotenuse is by either getting, Have you guys got your dividers still from your drafting class? Thank you. So some of you do. So you have dividers. You could now measure that distance physically on your graph, and you could get your protractor out and measure that angle. Or you could plug it into your calculator and say 5,000 squared plus 1,000 squared square root. Now I have my distance. Question? So now, no, the angle, so the angle here, if we look at this, so the sum of those two angles is not necessarily going to be, it may in the limit give you minus 180, but in between, those angles may not give you 90 degrees. For example, if I look at what's happening at DC from the poles, this guy is going to be, let's say that those were at minus 4,000 plus J4000. It'll make my discussion easier. This angle would be minus 45. This angle would be plus 45, and they would cancel each other out at the origin. Then if I moved straight across, then that one would give me 0, and this one would not be giving me 90. So they don't have to sum to anything in particular. It's going to depend on where they are located as to what angle they contribute. But you need to look at both of those to give you the effect of that complex pole pair. What if we look at the upper pole? Is this making sense? Whoa. Wow, let's review. Okay. Uh-oh. All right, I jumped a day. We were really reviewing. So now we've reviewed Tuesday and Thursday's class. I have no idea what I clicked to make that happen, but let's look at the upper pole. And now we have something here, let's say, and we're interested in j omega in general. And so our factor now is j omega plus 3,000 minus j 4,000. So this is j 4,000, and this is minus 3,000. And we want to know, really, what is happening between there and here. So that our angle, we could view it as a negative angle. This is now our theta P1, and our distance is L sub P1. But we could get there from our x to our j omega if we simply look at this expression. If we say, oh, let's go down 4,000 in the vertical direction. That's the minus j 4,000. So this piece, I don't know if this notation is going to make any sense, but let's say now we travel down here, and there's 1. Then we go over 3,000, positive. So that's 2. And now our third piece is up omega. So now in rectangular movements, we've gone from the pole location to the point in question, j omega. And that's the same as going along that effective hypotenuse, L sub P1. Meaning, the vertical distance that we've displaced is simply this, whatever this omega is, minus 4,000. That we just need this distance vertically, and we need this distance horizontally. And that will give us the hypotenuse of that triangle. Is that okay? Or clear? So that if we wanted this L sub P1, that's now the length of j omega plus 3,000 minus j 4,000, and the angle is the inverse tangent of omega minus 4,000 over 3,000. And if omega happened to be 10,000, then we would be looking up to find that location. And here we would simply have 6,000 in the vertical direction and 3,000 in the horizontal direction. And that's now how now what do we need to do to put all of those pieces together? We now have lengths and angles for each of those factors. If we wanted H, let's say H of J 5,000, it's going to be 1,000 times L sub z at an angle of theta z over L sub P1 at an angle of theta P1, L sub P2 at an angle of theta P2, and now we can multiply and divide those numbers, if they're in the numerator and denominator, and add and subtract those angles, depending on where they are, to obtain the eventual complex number graphically for the transfer function. We'll start at that point or somewhere close on Tuesday. This will be on the test.